By the way, do you mind to share the screen?
Yeah, sure. Let me do that. Can you see everything?
Okay, so we should start. Welcome everyone to Harvard CMS Quantum Matter in Math Physics seminar series. We are very happy and delighted to invite Brendan Rayhaun from YITP. He will be speaking about his recent work on the small Bosonic CFTs, Chiral Fermionizations, and the Symmetry Subalgebra Duality. And there was a previous talk given last week on the related topic, and stay tuned for the further other future talks on something similar related. And let me remind the audience, please feel free to interact with Rayhaun and ask questions. And we should welcome Rayhaun. So yours, please. Thank you.
Great. Thanks very much, Juven, for the invitation to speak here. I'm excited today to tell you about two relatively recent papers. One was done in collaboration with Sunil Mukhi, who's pictured here. And the second I submitted to the archive a little bit earlier this year, and it was a sort of follow-up to this original paper with Sunil. And I should say right from the outset that this second paper was submitted in coordination with two other groups on the same day to the archive. One was a group of mathematicians, and the other was a group of physicists. And we had the pleasure of hearing from Gerald and Sven last week in this same seminar series, and maybe we'll hear from the other group as well soon. So just to say, if you did attend the talk of Sven and Gerald and you're worried that you'll hear the same thing twice, I can assure you that that will not be the case. Any fear that I might have had that my talk is redundant was sort of assuaged within the first few minutes of listening in, which just speaks to kind of how many different and complementary perspectives there are on this material that I'm going to be telling you about today. Great. So in particular, I highly encourage sort of reading their papers and watching their talks because they're all very beautiful and nice. And as a final note of kind of logistics, let me just apologize at the beginning because apart from sort of pointing out the places where I will overlap with these other groups, I won't be very good about references just because there were simply too many to sort of keep track of. Okay, great. And with those administrative notes out of the way, we can get on to the physics. So this talk is going to be about informal field theories in low dimensions with small central charge and with relatively simple operator content. So in particular, I'm going to take the liberty to assume as many adjectives and qualifiers as are needed in order to make various classification problems tractable. But as I hope to convince you, we'll still be able to make contact with fairly non-trivial results. And so let me just, at the beginning, give you a bird's eye overview of some of the main results. And if you fall asleep within the first 5 minutes, you'll at least be able to walk away with these slogans. So the talk will be structured into 3 parts, and sort of within each part, I'm going to explain a kind of general strategy or a general approach to a classification problem of a particular kind. And then as a proof of concept, I'm going to use that strategy to basically classify a special class of, say, CFTs or something like that. So in the first part, which is going to be the bulk of the talk, I'm going to review a few general methods, including modular bootstrap, the current algebra bootstrap, and so-called gluing principle. The modular bootstrap is perhaps the most familiar of these three. It is a kind of program which attempts to capitalize on the fact that the genus one partition function of any conformal field theory satisfies modular invariance, and this imposes very strong constraints on the energy levels, if you will. The current algebra bootstrap is sort of related. It attempts to really leverage the power of continuous global symmetries to constrain the dynamics of 2D CFTs. And this final thing is maybe the most novel. And I'll explain how this so-called gluing principle ultimately leads to statements like every CFT of a particular kind can be expressed as a coset. If that word is unfamiliar to you, I'll define it later. Great. So using these three general methods, I'm going to kind of sketch for you how one can obtain the classification of most bosonic unitary 2D conformal field theories whose central charge is less than or equal to 24, and which have at most 4 primary operators. Okay, so that's sort of the first main result. And arguably more interesting than the result itself are its two corollaries or applications. So the first one is going to be that using techniques of fermionization and bosonization, one can actually translate the kind of result that I mentioned on the previous page, which concerned bosonic CFTs, to a classification of fermionic CFTs. In particular, the particular kind of fermionic theories that we'll be able to classify are so-called chiral fermionic CFTs. So theories that are purely consistent just using left-moving degrees of freedom without any need for right-moving degrees of freedom. And it's in this part of the talk, this part 2 of the talk, where I'm going to primarily overlap with the other two groups that I mentioned on the first slide. And finally, in the third part, this second application of the main result will be to generalize global symmetries. And the method I've been calling symmetry subalgebra duality, but I've been realizing more and more that it's closely related to sort of pre-existing ideas which come from symmetry TFTs, or also called symmetry topological order. But in any case, I'll use such ideas to essentially classify certain generalized global symmetries of chiral bosonic CFTs. Okay, so these are somehow the main results.
Excuse me, I have a question. This for bosonic result is non-chiral, right? Your result is not don't have to be chiral.
Yeah, that's right. Ultimately, it's going to be some kind of statement about non-chiral theories, but really, I'm going to be mostly working at the chiral level. It just so happens that the chiral algebras that I'm going to be working with are so simple that it's very easy to kind of glue them together to form non-chiral theories.
I see.
I'll comment more about this.
Okay, thank you. Yeah.
Great. Any more questions? Okay, so I'll dedicate one slide to mainly reminding myself why study. Sorry, what was that?
I wonder, I just make sure the previous talk by Sven and Gerard is they restrict to primary field, just one primary field, is that right? And you consider possibly more, that's so equal to 4?
I'm making the same restriction as them. So these fermionic theories that I'm classifying are the exact same theories that they're classifying. We'll see that they got a little bit higher. They got to C less than or equal to 24. But the constraint of one primary field is sort of implicit in the fact that I'm calling this a chiral CFT. So it's a fully consistent theory. It means it has one primary. If there's more primary operators, then you need to sort of incorporate right-moving degrees of freedom to make it a consistent fermionic CFT, or you have to kind of attach it to some kind of bulk spin TQFT, if you like, which is non-invertible. So.
Okay, thanks. And the previous the constraint for the rank smaller or equal to 4 is for the bosonic CFT, is it?
Yeah, that's right. So yeah, part of what I hope to show you is that having control over bosonic theories with at most 4 primary operators is sort of not quite equivalent to, but a special case of that is having control over fermionic CFTs with like 1 primary operator in the NS sector, if you'd like.
Okay, thanks.
Yep. Great. Any more questions before I move on? Right. So why study two-dimensional conformal field theory? Well, sort of all the things that the conformal bootstrap people will tell you apply here as well, in my opinion. But there are certain things that are special to 2 dimensions, which make studying 2D CFT particularly rich and interesting. So obviously there's the sort of increased tractability of working in low dimensions, which you may hope will help to learn general lessons about quantum field theories in higher dimensions. Famously, 2D CFTs arise as ingredients for describing string theory from the perspective of the world sheet. They're related to gravity also in a slightly independent way, namely by the ADS CFT correspondence. And here I'm being a little bit liberal about what I call ADS CFT. And in particular, I want to include things that don't look like semi-classical Einstein gravity in the bulk. So I have in mind sort of more exotic toy models of gravity that involve things in the bulk that look closer to topological field theory rather than gravity. Structures that are very closely related to 2D CFT are very important for various programs in pure mathematics. Some buzzwords here are moonshine, Langlands, category theory, so on and so forth. And finally, also a very interesting application of 2D CFTs is that they're useful for describing higher dimensional quantum field theories as well, usually with some extended amount of supersymmetry. So there they arise as encoding kind of certain protected sectors of observables that are protected by supersymmetry. The canonical example of this is that there's some certain class of BPS operators in 4-dimensional n equals 2 superconformal field theories, which have a kind of closed operator algebra amongst themselves, and that operator algebra forms the structure of a chiral algebra. Okay, and I won't talk too much about these applications in detail, but hopefully you'll get the sense that the theories that I'm going to be describing are closely related to a lot of these bullet points here. Great. Okay, so I see there's a question. Can you explain briefly what moonshine means? Yeah, so I think moonshine is a very fungible word, but roughly speaking, moonshine sort of refers to various mathematical connections between automorphic function theory or number theory and basically algebra, primarily finite group theory. And oftentimes the explanation for these connections involve exotic conformal field theories or chiral algebra. So the sort of canonical example of this is the monster CFT, which gave the explanation for why there's a connection between the monster finite group, which is some kind of exceptional finite group, and this very distinguished modular form called the J function. There's more examples like this, but that's sort of roughly what I had in mind. Great. So So as I said, my interest is in classifying conformal field theories. But you can't just sort of go out and try to classify all conformal field theories. You have to divide the problem into more bite-sized chunks. And one natural way to do this comes from thinking about the renormalization group flow. So a question that we often ask in physics is, given a UV CFT, which is perturbed by relevant operators, what does the theory look like at low energies? What is the IR CFT? And this is a difficult question to answer in general, but there are sort of very famous constraints. The main one being Zamolodchikov-C theorem, which says that the central charge in the IR must be less than that of the UV. So in particular, if you had a kind of list of CFTs whose central charge is less than CUV, well, that would be a list of, that would be a sort of menu of possibilities for what this IR CFT could be. So in particular, this kind of suggests a classification program where you try to enumerate conformal field theories in order of increasing central charge. So let's see how far we can get in that program. Okay, you start off very strong. Quite famously, it's been known for quite some time that all the conformal field theories with central charge less than 1 have been classified. These are the so-called minimal models. There's discretely many of them, starting with the Ising model at central charge 1/2 and going on to the tricritical Ising model and so on and so forth. This list of central charges accumulates at c equals 1, where something somewhat drastic happens. There's an entire conformal manifold or an entire continuous moduli space of CFTs that you get with central charge equal to 1. Conjecturally, we know all of them. So I've sort of included this figure here, which conjecturally captures all of the known c equals 1 CFTs. But as far as I'm aware, this is just a conjecture and it hasn't been put on any kind of mathematically rigorous footing yet. So if c less than 1 is a proof, c equals 1 is a conjecture, I claim that for c greater than 1, we know as close to nothing as possible. And the reason for this is that even sort of the most coarse questions that you might hope to ask don't really have any answers, and moreover, we don't even really have any expectations for what the answer should be. So for example, one question you might ask is there a gap between c equals 1 and the next value of the central charge, which is realized by a 2D CFT? Or is there a continuum of central charges above c equals 1? Is there an accumulation point from above? Somehow, none of these answers, none of these questions have clear answers. So just organizing the classification by central charge is not enough. We should sort of refine our question a little bit more. And in order to describe how we're going to do that, let me remind you about some basics of 2D CFT. So part of what makes two-dimensional conformal field theory very tractable is that they always come equipped with infinite dimensional symmetry algebras, which I'm going to call a chiral algebra. A mathematician would call it a vertex operator algebra, or a VOA. And essentially, these are the kind of subspace of holomorphic local operators of the theory, which form a kind of closed subalgebra. This is, the chiral algebra is always non-empty. For example, the stress tensor is always inside of it. And more generally, the sort of operator products of the stress tensor with its various derivatives all belong to the chiral algebra as well. And they generate a Virasoro subalgebra of V. Another kind of universal entry that you get inside of the chiral algebra is a so-called current algebra. And the idea here is that somehow, in general, when you have a continuous global symmetry, you expect by no other's theorem to get conserved holomorphic no other currents. And the sort of chiral algebra that they generate, or the subalgebra of the chiral algebra that they generate, is fairly universal. It's essentially completely determined by the structure constants of the corresponding Lie algebra, these FABCs, and a single positive integer k, which is called the level. So as a bit of notation, let me just say that I'm going to denote the chiral algebra generated by no other currents corresponding to a simple Lie algebra of type X and rank R, and with level K, I'm just going to call that XR sub K. Great. And now, whenever you have a symmetry in physics, you should try to understand how to organize the observables of your theory in terms of its representations. And you can do this, you can apply this to the Hilbert space of a conformal field theory. And in particular, you can decompose it into irreducible representations of the left and the right moving chiral algebras. You get a decomposition which takes this rough form. And we're going to restrict attention in this talk to conformal field theories for which the number of representations which appear in this decomposition is finite. So I'm going to call that number P, the number of irreps which appear in this decomposition. And when P is finite, that's a kind of theory that physicists tend to call rational. And one reason for this is that the central charge and the conformal dimensions of various operators are always rational numbers. And one of the reasons that it's natural to not only organize the classification of conformal field theories by the central charge, but also by the number of primary operators, is that conjecturally, there are a finite number of CFTs with a fixed C and a fixed P. So somehow, by fixing C and fixing P, we expect to recover a finite classification problem that we might hope is tractable. Yeah, so let me christen our goal with a name. We'll call it the CP classification problem. And that problem is simply to classify the finitely many CFTs which have central charge less than some fixed number C star, and with a number of primary operators which is less than or equal to some fixed number P star. Are there any questions about what our goal is?
I have maybe a naive question. I think earlier you tried to relate UV CFT and IR CFT through relevant perturbations or relevant operators.
Yeah.
But in some case, there could also be non-perturbative, maybe naive-looking irrelevant operators that can connect different CFT as some deformation class of more relate different CFT or relate different quantum field theory. So I wonder whether this statement is crucial in your classification.
No. This was kind of motivational, if you'd like, to inspire why one might care about a classification of conformal field theories by central charge, but I'm not going to use any sort of assumed properties about the renormalization group flow.
Okay. Yeah, sometimes maybe different CFT may not be connected by relevant, may not be deformed by relevant operators, but it could also deformed by some non-perturbative interactions, non-perturbative irrelevant operators. I don't know whether you know symmetry mass generation, that type of effects.
Symmetry generation. Well, sorry, I'm not really. I mean, I know this phenomenon of dangerous irrelevance. Is that what you're sort of referring to? Maybe?
That's one way to say it.
Yeah.
But it will not be anyway. So it's not something you will need to concern.
Yeah. It's not something I'll be that will be crucial. Yeah. Okay, so it'll actually be useful to not just sort of keep track of P, the number of primary operators, but to further keep track of sort of the entire representation theory of V. And the representation theory of V, it turns out, can be kind of efficiently encoded in this abstract mathematical structure known as a modular tensor category. And it truly is a refinement of P because P can be kind of recovered from this modular tensor category as its rank. If you don't know what a modular tensor category is, that's fine. So physicists tend to be more scared of category theory, but maybe that's changing in recent times. Physicists can sort of think about what the C is as it's the kind of bulk 3D TQFT which supports the chiral algebra V on its boundary. And this is kind of in the same spirit as the most famous example of this, which is that when V is one of these current algebras or one of these WZW algebras, then the bulk 3D TQFT is essentially Chern-Simons theory. So whenever we have a chiral algebra, we'll sort of be careful to keep track of the bulk TQFT that is kind of implicitly there. And the reason that I like to carry around this structure is that it leads to a kind of conceptual clarification about what doing rational conformal field theory involves. So in particular, defining an RCFT involves kind of two ingredients. So the first ingredient is you pick a chiral algebra V, which serves as the kind of sector of holomorphic local operators of the theory. And in the second part, so remember, the chiral algebra is not enough. You have to sort of glue a left and a right moving chiral algebra together to produce a full modular invariant CFT, like I've done here. And that gluing can sort of be visualized using this picture here. So here what I've done is I've sort of, this picture is due to Capusta and Salino, but you've sort of extended the 2D field theory into a third dimension. In the bulk lives this 3D TQFT, which I mentioned. And on the two boundaries, you place the left moving chiral algebra and the right moving chiral algebra. And sort of their different representations are stitched together to form a full modular invariant CFT using a topological surface operator that you place in the middle. And one nice thing about this picture is that it makes clear that this topological surface operator doesn't really depend on any details of the chiral algebra V. Rather, the only thing it cares about is this bulk 3D TQFT on which V lives on the boundary of. So the upshot of that is that sort of once you classify surface operators for a fixed 3D TQFT, you kind of know something about the different modular invariants for a bunch of different chiral algebras, all the chiral algebras that can form the boundary of this 3D TQFT, which there are infinitely many of. Okay, so some terminology. I'm going to call this tuple consisting of the central charge C and the modular tensor category script C or curly C. I'm going to call that the genus of the chiral algebra V. So we're going to organize theories by their genus throughout this talk. Great. So let me give you maybe an example of a kind of classification result, which is a classification of theories which live in a particular genus. So let's look at the simplest case where the bulk TQFT or this modular tensor category is trivial. So in that case, there's one primary operator. It's just the identity operator. And I'm going to somewhat abusively call these chiral CFTs. And the idea is that the reason that you can call them chiral CFTs is that when there's only one primary operator, the partition function or the character is essentially modular invariant already up to a phase at least. And so you can kind of think of the theory as being a completely consistent CFT in its own right, using only left moving degrees of freedom without having to pick a right moving sector. So we call these chiral CFTs. And here's what we know about them. So essentially by constraints of modular invariance, we know that their central charge has to be a multiple of 8. So the first non-trivial one you get is at C equals 8. Namely, it's one of these current algebras or WZW models based on the exceptional Lie algebra E8 placed at level 1. This is the unique theory at C equals 8. At C equals 16, there's two theories, and this is familiar to anyone who's studied heterotic string theory, where these two Lie algebras, if you like, are the gauge groups of the two 10-dimensional heterotic string theories. At C equals 24, it's almost been proven up to showing that the unique CFT without any continuous global symmetries is the monster CFT. So up to proving that fact, it's known that there are 71 theories. For example, 24 of them are essentially free boson theories in the sense that they're kind of built out of lattices. And then in general, you have some theories that are not free boson theories, but it turns out that everything can be obtained starting from one of the free boson theories, namely kind of the free boson theory made out of the Leech lattice and doing various ZN orbifolds, very cyclic orbifolds. Okay, great. So looking at this list, you might think you can continue on for quite some time. But it turns out that central charge 24 is where your luck runs out. And this is for the following reason. So at C equals 32, you can use this formula from the math literature known as the Smith-Minkowski-Siegel mass formula. And essentially what this formula does is it produces a lower bound for the number of so-called even unimodular lattices. So these are precisely the lattices out of which you can construct chiral CFTs. And it turns out that just by using this to kind of lower bound the number of free boson theories alone, remember, not every theory is a free boson theory, but just by lower bounding the free boson theories alone, you learn that there are more than 1 billion chiral CFTs at central charge 32. So there's very little chance of sort of explicitly classifying or explicitly enumerating chiral CFTs with central charge larger than 32. Although there are other more structural things that you can attempt to say, which I won't comment on in this talk.
Yeah, here I have a question. Does every lattice correspond to a CFT?
Yeah, every even unimodular lattice corresponds to a chiral CFT. Yes.
I'm worried about the it's not one-to-one, so maybe many different lattices correspond to the same CFT. So there's a maybe CFT is not as much.
Yeah, no, it turns out that different isomorphism classes of lattices produce different isomorphism classes of CFTs. Yeah,
I see. Okay.
So it sort of injects into the CFTs. Yeah.
Okay.
Yeah, I have a question here also. So I think this 24 is called Niemeyer lattice, right?
That's right. Yeah.
Lattice, and one of them is Leech lattice. But
right.
When you say everything is ZN orbifold Leech lattice, do you mean just from the Leech lattice or from the 24 of this Niemeyer lattices?
Just from the Leech lattice alone, you can do various ZN orbifolds for different values of n, and you can get everything. Yeah, it's actually a very simple story that I'm not going to get all the authors, but the one I know is Sven, who gave a talk earlier in this lecture series. It generalizes this interesting fact about the Leech lattice that all the other Niemeyer lattices are in some sense inside of it via this construction called the dipole construction. So this fact about CFTs is a kind of CFT generalization of that lattice fact. It's called, and so they call them generalized dipoles.
And also there's a fact, I think for C equal to 16 is that the EA times E8 and SO32, they are actually, there exists some deformation to relate the two seemingly different CFT. In the sense that if you view the two CFT living on a boundary of one high dimensional invertible topological field theory or invertible topological order in 2 plus 1D, then there exists a deformation only deform the.
I couldn't find anything like that in your home.
Yeah.
Sorry, you're. I think you said a word that is close to Siri, and it triggered my laptop. Sorry about that. Yeah. What were you saying? Sorry.
I said that there exists some 1 plus 1D deformation to deform this two different C equal to 16, seemingly different C equal to 16 CFT, the E times E and SO32, such that you don't need to change the 2 plus 1D bulk, the invertible field theory bulk, but there is some way to relate the two theory. So I think that's related to my previous question, say how do you count or classify CFTs here? There may exist some deformation to relate them. Do you count them differently? Do you
The deformation you have in mind that they're related by orbifolding? Folding?
No, it's not. I'm not sure it's orbifolding, but this is the process that you start with a CFT. And if you don't, depends whether you demand some global symmetry or not. But if you do, then all you are allowed to do is add in some possible interactions, preserve that symmetry. You are also allowed to bring down some heavy gap, high energy sector, preserve the same symmetry, and bring down them to interact, and then deform it in the sense aiding interactions. But that deformation will include more general, not just relevant perturbations or relevant operators, but you are allowed to aid, what we call symmetry mask generation, so other non-perturbating interactions. Then you can deform these two different, similarly different CFT.
I see.
And so E times E and SO32, I don't know, what spin 32 minus Z2, anyway. So these two CFTs actually are related, deformable to each other, while keeping the same bulk in 2 plus 1. So the 71 series, perhaps they are also deformable. I don't know how they are, probably they are all, yeah, maybe they are all deformed.
Yeah, it could be. I'm using a very that looks like a very coarse notion of equivalence of CFTs, and that it sort of identifies many different CFTs. I'm using a very fine notion of equivalence. Namely, I consider two CFTs to be different if their correlation functions and higher genus partition functions kind of don't always agree. So these two theories at C equals 16, for example, they have the same genus 1 partition function, but in general, their sort of correlators are different from one another. So I consider them to be different CFTs. They're just non-isomorphic to each other. If you like it, X operator.
Sorry, Juven, are you talking about a 3D interactions or 2D interactions?
2D. The bulk is the same. You just add interaction on the 1 plus 1D.
So you're talking about the existence of some UV theory that's non-chiral that flows to these chiral theories. Is that what you're talking about?
No, I said there exists some interaction between EA times EA. We'll start from EA times EA and possibly some boson, non-chiral boson theory, and interact with this EA times E8. And then there's a deformation that you can relate this to the SO32, or the one that you're writing down there. The two theories are deformed. They are in the same deformation class of quantum field theory. In a way, Cyber will call it deformation class of quantum field theory. I think he even mentioned this example sometime before in his string talk in 2019. Yeah. So anyway, it just depends on how do you classify. I don't know what I can interpret in a way. Say then probably you are saying that if there two different CFT are not deformable to each other under relevant deformations, operator deformations, then you count it differently.
No, I'm not. Maybe I misled with leading with the renormalization group flow and relevant deformations. I'm actually just
Yeah.
not thinking about deformations at all, sort of if the two CFTs on their own have like different correlators, then I consider them to be different. So deforming in the way that you're describing, I think does change various observables of the theories. And so that to me is an illegal way of identifying theories, if you like.
Mm-hmm.
Yeah.
So can you just last thing just point out what will be the difference between this 24 Niemeyer lattices type of CFT? What are the difference? Can I tell their difference from your data?
Well, generally, for example, they have different partition functions, different genus 1 partition functions. They for sure have different continuous global symmetry groups. They'll have different correlators of some kind. Yeah, they're just sort of different CFTs in the sense of their basic CFT observables, like scaling dimensions and OPs, basically.
Okay, thank you.
Okay. So, right. So more than 1 billion chiral CFTs of central charge 32. And so now I want to ask, like, what's a reasonable goal for this classification problem? So as we sort of just illustrated, in the particular example of chiral CFTs, if you fix a modular category, C, or fix a bulk 3D TQFT, then the number of chiral algebras which sort of terminate on that 3D TQFT grows rapidly with the central charge. And in general, you might expect that roughly at C equals 24, the number sort of explodes if you try to go too far beyond it. So we'll take this as a hint, and we'll just, we won't try to access CFTs above central charge 24. So that's the parameter C star in our classification problem. What about P star? Well, hopefully it's clear right now that classifying CFTs with at most P star primary operators is sort of at least as hard as classifying modular tensor categories with the same rank. And my understanding is that this has been achieved basically up through rank 5, although I've been told recently that there might even be results for higher values of P, but I have not found a reference for that yet. But in any case, I got tired at rank 4. So that's sort of where we're going to stop in this project. But I'll tell you later anyways why stopping at rank 4 is actually quite natural, at least if you're interested in fermionic CFTs, which we will be interested in later. So I'll sort of colloquially call CFTs that have a small central charge and a few primary operators, I'll call them small CFTs. So our goal is going to be to classify small CFTs. And this goes back to Xiaogong's earlier question, am I classifying chiral theories or non-chiral theories? Well, as I described earlier from that picture of Kapustin and Salina, there are two parts to doing CFT, classify the chiral algebras and then classify the modular invariants, which only depends on the modular category. And if you restrict to modular categories with rank less than or equal to 4, it turns out that sort of classifying the modular invariants or classifying these topological surface operators is more or less trivial. Generically, the categories essentially only have one, namely the trivial surface operator. And so essentially all of the complexity of classifying CFTs lies in classifying the chiral parts. And then you can always glue them together to produce a non-chiral theory afterwards. So sort of for the rest of the talk, I'm going to restrict to this problem of classifying chiral algebras with the understanding that after all the smoke clears, you can always reconstruct the full non-chiral theory if you'd like.
Excuse me, is that possible? You may have a P equal to 4 non-chiral theory, which is obtained from P bigger than 4 chiral theory.
Sorry, could you repeat the question one more time?
You know, So maybe some of a P equal to 4 non-chiral theory is coming from the gluing of a P bigger than 4 chiral theory.
Oh, I see what you're saying. Yeah. So good. Yeah, I'm going to good. I should have mentioned this, but I'm always going to be thinking about the maximal chiral algebra. So sort of all of the holomorphic local operators of the theory will be included in the chiral algebra. And under this convention, I claim that you're never going to get the phenomenon that you described, if that makes sense. So maybe as an example, you're thinking like D8 at level 1 is a P equals 4 theory, but it has a particular modular invariant that makes it E8 at level 1, which is a P equals 1 theory. But I don't allow that in my way of naming things because I'm in that theory, D8 at level 1 is no longer the maximal chiral algebra. The maximal chiral algebra becomes E8 at level 1. So
I see. So basically, your non-chiral theory have additional condition that is the maximum chiral one is 4.
yes, the
Okay.
maximum chiral algebra is 4. Yeah.
But there could be more general non-chiral theory with a 4 component basically.
I think that you'll see those sort of at lower values of P, I think.
Okay.
Yeah.
Okay.
I'm not sure if I'm being clear, but
yeah.
Okay. So with all that preamble, let me give you a bird's eye view of the results. So this table is going to take some time to explain. So this first column here is P, the number of primary operators. The second column here runs over all the modular tensor categories with rank equal to P. So for example, vec here is the category of vector spaces. It's the trivial MTC. It's the unique MTC with rank 1. And all of the rest of these, I attempted wherever possible to describe them in terms of Chern-Simons theory, basically, although that was not always necessarily possible. Now, the modular category determines the central charge of the theory, at least modulo 8. So I've written that number in the next column. And that means that since we're interested in classifying theories with central charge up to 24, for each modular category, there are sort of 3 compatible choices for the central charge. For example, in this P equals 1 case, C is equal to 0 mod 8. And so the 3 central charges are 8, 16, and 24. And so I write the number of theories in this genus as an entry in this table. So if you'd like, this 1, 2, 71 corresponds to the fact that E8 at level 1 is the unique theory with C equals 8. E8 squared and SO32 are the 2 theories with C equals 16. And then there were these 71 theories I mentioned earlier at C equals to 24. Okay, so maybe I won't go through these references in detail, but let me maybe just highlight stuff that's been done closer to the present day. So I will show ultimately how the bosonic theories that are kind of encapsulated by these maroon and yellow boxes. I'm not sure if you can see my cursor, but those bosonic theories ultimately will be related to fermionic theories by fermionization. And so because of this fact, the various people that have been studying fermionic theories over the years have sort of implicitly classified them, at least in the maroon. Those were sort of classified before this year. And then this box in the yellow, that is more recent and was those theories were classified sort of closer to this year. You'll notice that some of the entries in my table have skulls in them because I was not able to fully determine the theories there. But it turns out that if you want to know at least the skulls that are inside of these yellow boxes, you can go to Sven and Gerald's paper and reverse engineer from there. And so, oh, Boyle Smith. Yeah, my apologies. Yeah, I didn't include the full last name of one of the authors. And then, okay, so somehow the rest of the theory outside of boxes was part of what I tried to do in my most recent paper.
Sorry, there are two different. Are they the same yellow? They are yellow region.
Yeah.
They are the two. Are they working on the same yellow region? So just clarify the yellow.
Oh, sorry. The yellow highlight is different from yeah. The yellow highlight of the text is different than the yellow box around. It's uncorrelated to the yellow box around the theory around in the table. I just meant to highlight the fact that these are the two groups that I mentioned on the first slide. That's all. Yeah, thanks.
But sorry, but this is helpful. But this color corresponding to what the theory they are working on, is it, or not quite? You have
the depends on which color you're talking about, but yes. So like for example, this purple here. I don't know if you can see my mouse.
Yes.
This purple here means that these authors sort of worked on these theories outlined by purple in this table. Or this orange here means that me and Sunil worked on these theories here. Is that clear?
Yes, but you work on the full table, is it?
Yeah, the sort of everything that's not inside boxes is from my recent paper.
Okay. And how about the Boyle-Smith, the one you're trying to also point out?
Yeah, so they live kind of in this purple box.
Yes. Okay.
Or this maroon box. Yeah.
Thank you.
Yep. Okay, so I want to try to give you a taste for how you can generate such a table, generate such a classification. And one of the main tools that has been popular to use in this discipline is kind of ideas from the modular bootstrap. And essentially the idea here is that the characters of a theory, namely its sort of count of different energy levels in the different representations of a chiral algebra, are strongly constrained by these so-called modular covariance equations. And the details of this won't matter much, but the idea is that the characters of a conformal field theory form something known as a vector-valued modular form, which is a very rigid object. And so this has suggested a common strategy, which has been used over the years. So you try to fix P, and then try to kind of enumerate all the functions which satisfy the equations that I wrote on the previous page. And then kind of treat this as a proxy for the classification of rational conformal field theory. But I just want to point out that this isn't quite the same as classifying RCFTs for reasons that were sort of alluded to earlier. So one thing is that the characters are not perfect at distinguishing conformal field theories because of this fact that there exist chiral algebras which have identical spectra. So this is related to this mathematical phenomenon that you cannot hear the shape of a drum. In other words, the kind of spectrum of a Laplacian on two different shapes doesn't uniquely determine the shape. And here's two shapes which are not determined by the spectrum of their Laplacians. Here are two drums that you can't hear the difference between. But actually, before this example was known, funny enough, the two heterotic string theories were, I think, understood as an example of why you cannot hear the shape of a drum. Another reason that classifying modular forms is not the same thing as classifying CFTs is that there are modular forms which look completely healthy, but which aren't the characters of any conformal field theory. So for example, there's infinitely many functions which look like they could be the character of a C equals 24 chiral CFT, but we know that there are only finitely many of them, namely 71 of them. And so there's a big sort of discrepancy between the kind of admissible looking functions and the ones, the kind of CFTs, if you like. Nonetheless, it can be useful to classify modular forms as a bouncing off point for the classification of full CFTs. And so one small technical addition that we made was that we sort of solved the following problem. We classified all the possible functions, at least implicitly, that could describe the characters of any RCFT with at most 4 primary operators and with any central charge. And this is kind of relying on a very powerful machinery and theory of vector valued modular forms due to Bante and Gannon, which kind of distills this infinite dimensional space of functions down to a finite amount of data. And so basically, I set out to compute that data. So this is a very technical result, and rather than explain to you how it was derived, I'd rather like to show you how to use it to classify conformal field theories. So to do this, we have to also use some ideas from so-called current algebra bootstrap. And the idea here is that the operators of a Chiral algebra, which have conformal dimension equal to 1, can be thought of as no other currents. And therefore, their zero modes at least exponentiate to a continuous global symmetry of the rational conformal field theory. And more generally, their OPEs form one of these current algebras. And so we want to see how we can constrain this current algebra piece of the Chiral algebra. That's like a kind of first step, maybe, if you like, to determining the full Chiral algebra. And there's various pieces of input. So one is, if you happen to know the character of your theory, well, there's the sort of one of the coefficients of the vacuum character, of the character of the Chiral algebra itself, tells you precisely what the dimension of the global symmetry algebra is. So somehow you use the modular bootstrap, you cook up some characters, you know instantly what the dimension of the global symmetry algebra is of any CFT that has that character. Another fact is that the rank of this Lie algebra is constrained to be less than or equal to the central charge of the full Chiral algebra that it's sitting inside. And somehow the idea there is that a physicist would kind of intuitively think about this as, all the U1s inside of this Lie algebra can be bosonized to free bosons, and each boson contributes central charge 1. So the total number of free bosons better not exceed sort of the total central charge of the theory by unitarity, is the essential idea. And then finally, the levels, or maybe the last thing that we'll need to constrain. And in order to constrain the levels, you can simply argue that, again, the central charge that is contributed by this current algebra piece of the full Chiral algebra had better not exceed the central charge of the full Chiral algebra. And the central charge contributed by the current algebra piece involves the levels. So you get another constraint there. And so here's how this kind of plays with what one finds from the modular bootstrap. So what one finds from the modular bootstrap is that if you restrict to theories with central charge less than or equal to 8, and at most 4 primary operators, then within each genus, it turns out there's exactly one function, or at most one healthy function, which looks like a healthy set of characters for a Chiral algebra. And so immediately what you learn is that there's only one possible dimension of the global symmetry algebra. Maybe it's best to look at this in an example. So let's consider this particular genus. So we want to classify theories with central charge 7 and whose bulk 3D TQFT looks like Chern-Simon's theory of E7 at level 1. So by cranking the lever of the modular bootstrap, you find that there's exactly one sort of modular form which could describe the character of a theory in this genus. And from there, you learn that there are 133 no other currents in any putative theory in this genus. Using these dimension and rank constraints, you find that the only Lie algebra with dimension 133 and central charge less than or equal to 7 is none other than E7 itself. And then finally, you can use the level constraint to sort of constrain the level to be 1. So this, if you'd like, sort of proves that there's a unique theory in this genus, and it's the obvious one. It's just the current algebra E7 at level 1. And using kind of the same kinds of ideas, but in increasing levels of sophistication, you can churn out the entire classification of rational conformal field theories with central charge less than or equal to 8 and at most 4 primary operators. So here again, P is the number of primary operators, C is the modular tensor category. And along the right-hand side here, I've listed the theories in each genus. And it turns out there's one for each of these genera. And most of the time, they're sort of pure current algebras. They're pure WZW models. Other times, they kind of involve other ingredients. For example, here's the Ising model. Here's a free boson theory. And there's these kind of more exotic extensions of current algebras and things like this.
Sorry, Brandon. So you never find a case where the central charge of the full theory minus the Lie algebra part is greater than 1 or greater or equal to 1?
No. Yeah, no, it's always less than 1. So like, in fact, the only time it's not equal to 0 is here, where it's equal to 6/7.
And what about up to 20, just as a preview, when you go up to 24, do you have these cases?
So as I'll describe in a moment, I didn't try to, these cases, you mean like where the current algebra doesn't,
If the difference is less than 1, then we know it has to be a Virasoro minimal, like L type. But if it's greater or equal to 1, then
yeah, great. Yeah, when you go past C equals 8, then it turns out the difference is greater than 1 sometimes. Yeah, although not that often, but it is. But by virtue of what I'm going to tell you in a minute, you can still determine what that piece is. It turns out that they're always kind of these like W algebra-y things, or like cosets of Kac-Moody algebras, basically.
Okay.
Yeah. Okay, I'm not doing great on time, but I was told that I can go for 2 hours. So I will push the limits of the audience attention span a little bit. So as I said, it's sort of too hard to continue to use the methods I described previously to classify theories with C greater than 8. And so we need to use new methods. And a crucial ingredient that we'll make use of is the idea of coset conformal field theory. And the way that works is given some chiral algebra V and some subalgebra inside of it, you can always kind of define a new chiral algebra from that. And it simply consists of all the operators in the bigger theory that commute with the operators inside of the subalgebra. So this is called a commutant by mathematicians. It kind of generalizes the idea of a centralizer inside of a group or Lie algebra or something like this. And there are sort of famous examples. For example, I think this one may have been the first. If you take the theory upstairs to be product of SU2 level K models and the theory downstairs to be SU2 K plus 1, then it turns out that this gives you a kind of coset construction of the minimal models, of all the minimal models of A type. Okay, well, okay, so how are we going to use this? So here's some basic observations that are going to turn out to have kind of nice consequences for us. So let's say you fix some seed chiral algebra W in some genus. And let's say that your goal is to then classify all theories that belong to a complementary genus, by which I mean a genus where the modular category is sort of like the complex conjugate of the modular category of your seed chiral algebra W. Well, any chiral algebra W twiddle in this complementary genus can be glued to W to obtain, if you'd like, a P equals 1 theory, a chiral bosonic CFTV with central charge equal to the sum of the central charges. This is very similar to constructing a non-chiral theory using like a diagonal modular invariant. It's just that here we're sort of only using left moving pieces as opposed to right moving pieces. It just so happens that this W twiddle kind of has a modular category which is the same as the complex conjugate of W, if you'd like, but it's otherwise completely left moving. Going in the other direction, if you know that a V has been obtained by gluing chiral algebras in this way, then you can always reconstruct this W twiddle using basically this coset construction. So in here, W twiddle is precisely all of the operators in V, which commute with the operators in W, if you'd like. And here's the upshot. So the upshot is that once you know even a single example of a theory in some C genus, then in principle, you can enumerate all the theories in a complementary genus by enumerating cosets of this form that I've written here, where here again, V runs over P equals 1 theories, chiral bosonic CFTs, and iota runs over all the different ways of embedding this W into V. And there are a few reasons why this turns out to be a tractable problem. So the first is that, as I previewed earlier, chiral bosonic CFTs, we know a lot about them. And in particular, they've been classified through central charge 24. So that sort of, we know all the V's that we have to take. We also kind of have seed chiral algebra for each modular category with rank C less than or equal to 4. That was this table over here. These are all of our seeds over here. And finally, the most difficult part of this is enumerating all the different ways of embedding the seed into, into V. But there's a very happy simplification that occurs for the particular choices of seed that we have, which is that they're almost always a kind of like current algebra. And enumerating embeddings of current algebras is much, much easier than enumerating embeddings of kind of more general chiral algebras. And the reason is that basically you can always reduce the problem of enumerating embeddings of current algebras to a problem of just ordinary Lie algebras, which is a very classical problem that is very soluble. So this is tractable and effective. And maybe I won't go through this example, but let me just flash this table here to say that really this formalism allows you to compute kind of everything that you would want to. So here I'm enumerating theories whose bulk 3D TQFT is Chern-Simons theory of F4 at level 1. And to do that, I basically have to study all the different ways of embedding this seed theory G2 at level 1 into the different chiral bosonic CFTs. So for example, if we look here, you can embed G2 into E8 squared. You can embed G2 into SO32. And these are the only two ways to do this. And correspondingly, the cosets are the two theories, in this particular genus. And the coset is not a very direct description of what the theory is, but this is just to show you that you can get very sort of explicit descriptions, at least of a subalgebra that is conformal, and that's often useful enough to completely determine the theory. And you can compute sort of the characters fully; those are reported over here, and so on and so forth. So here are some examples where the central charge is the difference between the central charge of the full theory and the current algebra is greater than 1. But in these cases, it just so happens that you get a product of minimal models, for example.
What is boldface S?
Oh, S means Schelikins. So yeah, sorry, I should have mentioned, but basically the way that the C equals 24 theories work is that they're completely determined by their Kac-Moody subalgebra. And so basically I'm identifying each theory by its corresponding Kac-Moody subalgebra. So S E63 G21 cubed is the unique C equals 24 chiral CFT with that corresponding Kac-Moody algebra, basically.
But okay, so if someone understands your method like this, it goes without saying that this is the shell, because it has to be a chiral bosonic theory at central charge 24, right? Like this boldface S, even if you did not write it, it would still be like self-explanatory.
Yeah, I just didn't want to write E63 G21 cubed without the S in front, because the numerator isn't E63 G21 cubed, right? That's not a chiral CFT, but rather it's an extension of that.
Right.
It's a conformal extension of that. That's why I write S, yeah.
I have another question. So suppose there actually existed a second theory that has the same, has J function as character. Would you say that the classification would possibly be missing stuff from C, from 8 to 24, or just at 24? Like there's just this, you just missed something at 24.
You're asking like how much my results rely on the uniqueness of the monster CFT?
Yeah.
Yeah, it turns out that my results do not in any way, shape, or form rely on that. And the reason is that sort of always the seed chiral algebras have currents, have continuous global symmetries. And so even if there were another theory with J as its partition function, it wouldn't have any currents. And so my seeds couldn't embed into it. So if you'd like, yeah, like for example, nothing here is ever going to be a coset of the monster CFT because I can never embed my seeds into the monster CFT. And likewise, nothing here is going to be a coset of any other thing with partition function equal to J because I can never embed my seeds into that thing either, whatever it is.
Okay, yeah, that's very clear. Thanks.
Yeah, great. Okay, so that's part one. And the other two parts are much shorter, but if it's okay, I want to take a quick 2-minute break to use the restroom.
Yes.
Great, I'll be right back. Sorry about that. Yeah, maybe it would be a good time to pause for questions as well. Okay. Great. So so part two is about classifying fermionic CFTs using ideas of fermionization and bosonization. So let me now explain that. Actually, let me plug myself in first. So I think I'm going to be belaboring the point here, but let me make a quick digression to make an analogy with orbital folds. So let me just point out that there are two things that one might mean by taking an orbital fold. So usually when a physicist thinks about orbital folds, one thinks about a procedure which takes a modular invariant CFT and a non-anomalous symmetry group G and produces a new theory out of this pair, essentially by gauging G. At the level of the Hilbert space, the words are that you sort of first restrict to the operators which are invariant under the action of G, and then you add in various twisted sectors, essentially to make the resulting theory modular invariant. On the other hand, a mathematician is maybe a little bit more flexible in what their definition of an orbital fold is. So their input is a chiral algebra, which is not necessarily modular invariant, and a symmetry group, which is not necessarily non-anomalous. So in other words, it may have an anomaly. And from this pair, they produce a new chiral algebra. Namely, they consider sort of the subalgebra consisting just of the fixed points of the action of G. So here we sort of skip the part of adding in twisted sectors. We only restrict to G invariant states, and that's because the thing that we want to get on the other side is not necessarily a modular invariant CFT, but just another chiral algebra. And these two notions of orbital fold are related to one another, because if V is the chiral algebra of some conformal field theory T, then the mathematician's orbital fold will be a subalgebra of the chiral algebra of the physicist's orbital fold. That's a bit of a mouthful to say, and maybe requires a little bit of thinking, but maybe this is just to say that they're not completely separate from one another. A similar thing is true for bosonization and fermionization. So a physicist might call bosonization the following. So one takes a fermionic conformal field theory with the particular constraint that the left minus the right moving central charge has to be a multiple of 8. So there's some constraint on the gravitational anomaly. And okay, that a fermionic CFT in general depends on spin structures. But if you sum over the spin structures by performing a GSO projection, then you produce a bosonic CFT. So if you'd like, this is sort of like doing a physicist's orbital fold, but applying it to this special symmetry that all fermionic theories have, namely -1 to the f. And an example is that although the two are often conflated, the Ising model is not the same as a fermion. Rather, it is the bosonization of a non-chiral Majorana fermion. On the other hand, there's a notion of bosonization that might be more natural to mathematicians, which is you take a fermionic chiral algebra, let's say in the NS sector, that can be decomposed into two pieces, one consisting of the operators with integer conformal dimension or integer spin, and one consisting of the operators with half integer spin. And the operators with integer spin form a subalgebra of the full NS sector operator algebra. And in a sense, it's a sort of bosonic subalgebra. So we call the bosonization of a fermionic Chiral algebra simply the subalgebra of operators which have integer spin, because that's a bosonic object. And if you'd like, this is sort of like the same thing as a mathematician's orbifold, but again applied to -1 to the f. And there's familiar examples involving a chiral fermion and the chiral algebra of the Ising model. Again, so there's maybe I won't go over the physics definition because I'm only going to use the math one, but there's a notion of fermionization as well, which sort of is opposite to bosonization. And for a mathematician, one would sort of take a bosonic chiral algebra, but it can't just be any bosonic chiral algebra. It has to specifically be a chiral algebra with a particular constraint on its modular tensor category, or rather its bulk 3D TQFT. And in particular, what this constraint says is that this 3D TQFT, or this chiral algebra, should have a kind of a privileged object called V1, which is fermionic in the sense that it has a conformal dimension, which is a half integer, and it satisfies this kind of fusion rule. So you can also translate this sentence into a statement about the bulk 3D TQFT having a privileged line, topological line operator. And the idea is that once you have such an object, you can always sort of combine it with V0 to produce a fermionic chiral algebra. And okay, well, here's how you use these methods for classification. So first of all, bosonization and fermionization are kind of inverses to one another. And so in particular, most of the time, if you have a question about fermionic theories, it can sort of be recast equivalently as a question about an equivalent bosonic theory. So if you're scared of fermions like me, you can always kind of work bosonically for most of the problem and then go back to the fermionic description at the end using fermionization. And so that's exactly what we'll do. We'll sort of classify chiral fermionic CFTs by bootstrapping their bosonizations, their bosonic subalgebras. And the reason that this plays very nicely with the bosonic classification results we produced earlier is that there's a kind of coherence between the representation theory of the fermionic theory and that of its bosonization. And a special case of this that we'll use is that in the particular case that this VNS is the NS sector chiral algebra of a chiral fermionic CFT, meaning a fermionic theory with one primary operator, if you'd like, then it follows that its bosonic subalgebra has a bulk 3D TQFT, which is essentially determined entirely by the central charge C. In particular, it is the same 3D TQFT as spin n at level 1, Chern-Simons theory. And it turns out that Chern-Simons theory always has rank 3 or 4. So in other words, the bosonic subalgebra of a chiral fermionic CFT always has at most 4 primary operators. And therefore, if VNS is a chiral fermionic CFT with central charge less than or equal to 24, then its bosonic subalgebra must have arisen somewhere in our classification on earlier slides. And then conversely, you can sort of reconstruct the fermionic theory by fermionization starting from its bosonic subalgebra. So this is what we did. And so I was only sort of strong enough to go up through C less than 23. Sven and Gerald made it up through C less than or equal to 24. This other group of physicists went up through C equals 16. They have a very nice discussion on the relationship to non-supersymmetric heterotic string theories in 10 dimension. And in particular, they sort of elevated to the level of, I think, mathematical rigor, some results that were speculated to be true in the physics literature. Okay,
Sorry,
so
I have a technical question. So when you try to embed the Lie algebra inside, say, like a C equals 24 chiral bosonic theory, is your method completely like has nothing to do with, say, Katz's theorem? Is that right?
with what theorem?
Katz's theorem, like through looking at symmetries of the chiral bosonic theory. Your method is completely different. Okay.
Yeah, it does not involve that. The only thing I relied on there was that somehow like all the semi-simple subalgebras of Lie algebras of rank less than or equal to 8 have been kind of like classified. And there's a nice computer program which, you know, you give it a Lie algebra, it tells you all of the subalgebras. So you can kind of just programmatically enumerate embeddings in that way.
Yeah, but what is the method that program uses?
Right. I would be surprised if Katz's theorem sort of appeals to finite symmetries, right? Of
Yeah.
Okay, granted, I don't actually know what, you know, the details underneath the hood of that program, but I would be a little surprised if it went through Katz's theorem. But maybe that it'd be worth checking, yeah.
Okay. Because it seems that at the technical level, that's the main difference between your approach and like this other approach.
Yeah, I mean, right. I think the other approach is like spiritually similar to part 3 of my talk, which is symmetry, subalgebra duality. But yeah, but yes, I think if I were to summarize the difference, I would say that you guys work kind of fermionically throughout and I work bosonically throughout. So that's like,
but that I think is a bit super, well, that's on the surface, it looks like that, but at the under the hood, I feel like this class, how you go and look at the embeddings of algebras is sort of the key difference in the methodology.
yeah, it certainly could be that maybe our two methods merge if you look under the hood of this program.
Thanks.
Yeah. So I'll just give you an example. So here I report, just because these are the theories that fit onto a single page, I write down all the theories with C less than or equal to 20 and no free fermions, i.e. no dimension 1/2 operators. And the reason that it's kind of sufficient to restrict your attention to these theories with no free fermions is that if a theory did have n spin 1/2 operators, then it turns out that those n spin 1/2 operators generate a kind of decoupled free fermion sector. So your theory kind of trivially factorizes into a product of n free fermions and a kind of more interesting piece, V prime, which is a fermionic chiral algebra which does not have spin 1/2 operators. So I just kind of reported all of these choices of V prime with the understanding that if you want to get kind of the most general chiral fermionic CFTs, then all you have to do is take this list and kind of tensor arbitrary numbers of free fermions with them. And one thing that's kind of interesting is that sort of the first non-trivial theory that you get in the sense of not having any free fermions occurs at C equals 12. So you have to go to a comparatively high central charge. And this is actually a somewhat mathematically significant CFT, at least when you endow it with an n equals 1 supersymmetry structure, because its kind of automorphism group, which preserves that n equals 1 supersymmetry, is a kind of distinguished finite simple group called the Conway group. And here we see that we obtain a kind of large tower of theories on top of it, which in principle could also be of similar mathematical interest. In particular, whenever you have a theory which admits an n equals 1 supersymmetry structure, those have not been classified for these theories yet. But if you find n equals 1 structures for some of these theories, because they have no free fermions, it turns out that their n=1 automorphisms are always going to be finite groups. And so you can contemplate whether or not you'll make contact with sort of exotic exceptional group theory. Okay. So that's about all I have to say about fermionic chiral algebras. And in this last part, I'll try to speedily tell you about bootstrapping generalized symmetries. So just by way of introduction, let me remind you that say you have a U1 symmetry with a conserved current, then you can always produce from that a codimension 1 operator by integrating its Hodge dual over some codimension 1 manifold and exponentiating. And it turns out that the conservation of J, in other words, the statement that this U1 is a symmetry, implies that this operator is topological. Namely, you can deform it through partition functions, and provided that you don't push it through a charged operator, then the correlation function will not change. So if you take codimension 1 operators as the definition of what a symmetry is, then in addition to encountering these kind of group-like symmetries, you also encounter more exotic things like non-invertible symmetries. And in 1+1D, these global symmetries are described by topological line operators, and the mathematics of the various properties of a topological line, of a set of topological line operators, is basically the theory of fusion categories. So in other words, so this is not to be confused with modular tensor categories. They're related but separate things. Modular tensor categories describe the bulk 3D TQFT of a chiral algebra, the representation theory of a chiral algebra. And if you'd like, fusion categories sort of describe symmetries of 1+1D theories. And maybe somebody can correct me if I'm wrong, but I believe it's safe to say that there are almost no CFTs except for the minimal models for which the full sort of category of topological line operators is known. And part of the issue here is that sort of after C equals 1, these categories have infinitely many kind of independent line operators in them. So that makes them a little bit harder to study. A quick example of the simplest example maybe of a non-invertible symmetry is, okay, the Ising CFT famously has a Z2 spin flip symmetry. And what you can do is you can gauge this Z2 in half of spacetime. This produces an interface between the Ising model and its Z2 gauging, which it turns out is topological. But because by Kramers-Wanier duality, the Ising model is dualed to its Z2 gauged version, you can think of this interface actually as a topological line operator within the Ising model itself. And then you can use this to sort of go out and compute its fusion rules. And it turns out that both the Z2 line and this non-invertible duality line generate an example of what's known as a Tombari-Yamagami category. Okay, so this is just an example to convince you that these things exist and they're ubiquitous. So let me describe to you the main tool that I want to use to approach symmetries in 1+1D conformal field theory. And for simplicity, I'm going to restrict to chiral CFTs, symmetries of chiral CFTs, but I suspect more or less everything I say will have a suitable generalization. And in fact, I think the generalization will be quite interesting and related to other problems that condensed matter theorists are interested in, but maybe I'd be happy to talk about that more offline. So, okay, so as the name suggests, symmetry subalgebra duality is a kind of relationship between the symmetries of a 1+1D CFT and its subalgebras. So let me describe the map in one direction, the symmetry to subalgebra map. So you can always, given V, pass to the subalgebra of operators inside of V that sort of commute with the lines in this symmetry category F. So in other words, if you have an operator for which there is no penalty to drag the line L through it in blue, then that participates in this subalgebra, and every other operator you sort of throw away. If you'd like, you can kind of, well, sorry, I should say one interesting fact and one very useful fact about this subalgebra is that its bulk 3D TQFT, or its modular tensor category, is completely determined in terms of F via a construction known as the Drinfeld center construction, and it's usually written Z of F. So if you like, you can think about this pictorially as starting with your 1 + 1D chiral CFT V and coupling it to a bulk 2 + 1D gauge theory for F. That gauge theory is a TQFT, and so it should be described by some kind of modular tensor category. And it turns out that that modular tensor category is precisely this Drinfeld center. And it also turns out that this coupling of V to this bulk gauge theory essentially has the effect of projecting down to this this VF subalgebra, this subalgebra of operators which are kind of neutral under the symmetry. So this is the symmetry to subalgebra map. Going in the other direction, let's say that you're given subalgebra W. It turns out that it's embedding into this bigger chiral CFT V defines a topological boundary condition in its associated bulk 3D TQFT. And this topological boundary condition has a special property that if you take this subalgebra W, sort of extend it into 3 dimensions using its bulk 3D TQFT, and then terminate that 3D TQFT on the topological boundary condition on the other side, well, it's topological, so you can in particular kind of squish it down back down to 2 dimensions. And the theory that you'll get when you do this squishing is precisely this bigger theory V. And this has the interesting consequences, that any sort of topological line that can live on this topological boundary condition will become a topological line that acts on V. And if you'd like, kind of all the topological lines on this boundary can be obtained by taking topological lines from the bulk, which are just described by this bulk 3D TQFT, and kind of pushing them to the boundary. Of course, this map is not like one-to-one. A bunch of lines will go over to the same thing. So, but in any case, there's an algorithmic way to kind of determine what lines live on this topological boundary.
Wait, are you allowing subtractions?
Subtractions?
Yeah, because if you push a bulk line to the boundary, and often it'll be non-simple, and then to get a simple line, you have to like subtract things.
Oh, I see. Mathematically, what I'm making use of is that this boundary condition defines a Lagrangian algebra inside of this rep W, and the fusion category I'm looking at is the fusion categories of A modules, basically, inside of inside of rep W, which I believe should correspond to the sort of topological lines that can live on this boundary condition.
Well, let me put it another way. If you have an arbitrary blue line on the boundary, like a generic one, you cannot pull them into the bulk, right? Only specific combinations can be pulled into the bulk.
Oh yeah, I believe that's true. Yeah.
So when you say that you can get any line by pushing a line from the bulk to the boundary, I feel like you're allowing yourself to add and subtract things.
I
to
see.
Get the ones that cannot be pulled into the bulk.
Good. I might have been a little too sloppy then. What I didn't appreciate that there's this bulk to boundary map, and I think I was making some kind of assumption about like its injectivity or something, or surjectivity. But yes, sorry. So that actually doesn't matter. The only thing that matters is that any line that's supported on this topological boundary condition will become a topological line that acts on V. That's like the key point. Yeah, thanks for the clarifying comment. Okay, just a quick example. So consider the simplest symmetry, Vex Z2, which is the sort of fusion category that corresponds to a non-anomalous Z2 symmetry. It turns out that this E8 level 1 theory has a non-anomalous Z2 symmetry. And the subalgebra that's associated to it by this symmetry subalgebra duality turns out D8 at level 1. These are just the Z2 even operators inside of E8 at level 1. And pictorially, you can sort of think about coupling E8 at level 1 to the toric code in the bulk. And then on the boundary, what would be happening is that now there's this D8, this SO16 WZW model living on the boundary. Going in the other direction, say you didn't know that E8 had this Z2 symmetry, all you knew is that it had an SO16 subalgebra. Well, purely mechanically, you could construct a Z2 symmetry of E8 by decomposing E8 into representations of this subalgebra and simply defining this Z2 to act as +1 on the states in this first summand and as -1 on the states in the second summand. Or if you'd like, you can instead draw this picture. So, for example, take this 3D picture, the toric code in the bulk, the subalgebra on one side, and well, there's two flavors of topological boundary conditions of the toric code. Take the smooth one if you'd like, for example. It doesn't really actually matter because the two boundary conditions are related by electric magnetic duality, but take the smooth one. So the claim would be that if you collapse this picture, you go over to E8 at level 1. And the claim is that the smooth boundary supports a Z2 worth of lines. One way to see this is that if you sort of push the magnetic line onto the boundary, it condenses. And if you push either the E or the electric or fermionic lines in the bulk to the boundary, then they become kind of the Z2 line of this topological boundary. Okay, but how do you use this for classification? Well, and I'm almost done here. This is a very general statement. Any non-anomalous Z2 symmetry of E8 by this symmetry to subalgebra map would define a chiral algebra that lives in this particular genus. This genus with central charge 8 and where the bulk TQFT is the toric code. But the toric code has rank 4. So we certainly classified theories in this genus earlier, or we certainly claimed to, and it turns out that the only one is SO16, is D8 at level 1. And so because there's only one sort of chiral algebra that could play the role of the fixed point subalgebra of a non-anomalous Z2 of E8, that sort of proves that the Z2 that we discussed previously is kind of the unique one. So if you'd like, the name of the game is to classify generalized symmetries of chiral CFTs by kind of bootstrapping their associated subalgebras. And so here's just a kind of a catalog that you can get of symmetries of E8 of different ranks. The rank 2 entries are complete in the sense that every rank 2 generalized symmetry of E8 at level 1 occurs in this table. So it has exactly one non-anomalous Z2, one anomalous Z2, and one so-called Fibonacci category. That's sort of the unique non-invertible rank 2 fusion category. And here are their corresponding associated subalgebras. The higher rank cases are just examples of symmetries that you can get sort of combining symmetry subalgebra duality with the theories that we constructed earlier in this talk. They're not necessarily complete, although they might be. You can see you get a kind of variety of different symmetries. You get some cyclic group symmetries with various anomalies, some Fibonacci symmetries, some Tamari-Yamagamis, and it turns out there's this kind of interesting PSU27 non-invertible symmetry as well. And so I think this is kind of just the tip of the iceberg. I think there's a well-defined mathematical program where you kind of enumerate global symmetries of various 1 + 1D CFTs by rank, and it appears to be fairly tractable. And so I think it would be very interesting to obtain more data. Okay, so now we're basically at the end of my talk. So let me just quickly provide some future directions. So obviously, the methods that I have described are pretty general. So I suspect that you can certainly classify more bosonic CFTs by genus, more fermionic chiral algebras with more than one primary operators, more generalized global symmetries, and so on and so forth. I think structurally, there are some interesting questions lurking underneath the surface here, related to sort of estimating the growth of theories with central charge, if you say organize them by genus. I mentioned earlier that there's the Smith-Minkowski-Siegel mass formula, which essentially estimates for you the number of free boson theories in a given genus. And it's kind of interesting to contemplate whether or not there would be similar formulas governing the counts of more general chiral algebras by genus. Relatedly, the sort of chiral algebras that we construct here give you natural examples of ensembles of CFTs. And I think it'd be sort of interesting to investigate whether or not these have a holographic interpretation. And the preliminary guess is that the answer is yes, but I'm currently working on that. So hope to have more to say soon. As I mentioned earlier, for these fermionic CFTs, it could be interesting to try to classify supersymmetry structures on them. One reason for this could be if you're interested in moonshine, because n = 1 supersymmetry structures would lead to interesting finite automorphism groups. Another interesting potential application that Ng is very familiar with is to topological modular forms. I know less about that. Somehow, one very interesting question that I'd be very interested in the answer to is whether or not one could prove whether any two chiral CFTs of the same central charge are related by gauging a generalized symmetry. I'll just comment, like, why would you even expect this this statement to be true? Well, for one, it turns out by deep facts of mathematics that it's true for free boson theories. Any two free boson theories, chiral free boson theories of the same central charge, are related by a sequence of cyclic group gaugings. And it's also known to be true for general theories with central charge less than or equal to 24. So if you'd like, one motivation for trying to determine the answer to this question is that, in a sense, like the bosonic classification program that I've been pushing for proceeds by reducing the classification of all theories with p greater than 1 primary operators to the classification of theories with p = 1 primary operators. Earlier in the talk, I sort of had a pessimistic comment about how probably you can't get too far in classifying p = 1 bosonic CFTs, but there might be more structural things you could say, and this is one example of them, namely that they're all kind of related by orbifolding one fixed theory. Okay, and so that's all I have to say. Thank you very much.
Thank you very much. Thank you, Brendan. Question, comments from the audience?
Yeah, just echoing what Ying said. Somebody emailed me shortly after I posted my paper with the same comment that symmetry subalgebra duality is closely related to subvector theory. So yeah, I think I shouldn't have named it. I shouldn't have given it my own name, but I somehow didn't. I didn't know about its existence prior.
Are they the same thing?
Well, there's like two sort of complementary approaches to 2D CFT. One involves kind of vertex operator algebras. The other involves kind of like conformal nets. And they're like, okay, I know very little about conformal nets, but I believe that they're believed to be kind of equivalent, or at least very similar. And sometimes it turns out that the things that you can say about conformal nets are stronger than the things that you can say about VOAs. And in particular, I think people have formalized this notion of symmetry subalgebra duality in the context of conformal nets, and there it sort of goes through this object called a hypergroup, which I'm not that familiar with, but it's supposed to be closely related to fusion categories. So Ying, I don't know if you have any more comments on subfactor theory.
Well, I don't know it. I don't know enough of it to say anything too precise. But I think, as you said, like if you're given a VO, well, if you're given the CFT, then you can sort of think of it as a net of Neumann algebras, and then you can speak of like von Neumann subalgebras that have like some finite index in the full algebra, and then from that pair, which is called a subfactor, you can define a tensor category using like the module, like, and then like the various modules. So
Right.
Any question, comment? Let's see. You can still share the screen. Let me see.
Okay. Yeah. Sorry. No, I X'd out because I'm I'm worried people have run out of steam after 2 hours. But I blame you, Juven, for letting me go on for so long.
I don't want to see the screen again. I have a question though.
Oh, okay. I'll pull it up.
I can end it first.
Yeah.
Maybe we should thank Brendan first, and then people can stay to ask.
Oh, thanks everyone.
Any more question? Last question, comment? No. Okay. Thank you, Brendan.